colloquium of every Wednesday here in ICTP-SAIFR. So let me introduce our speaker, that today is Pedro Machado. He's currently a permanent investigator in the Theoretical Physics Division of Fermi Lab since 2017, right? Before that, he got his PhD nearby in USP, and he did one postdoc in Madrid, then one postdoc again in Fermi Lab, and then he became a faculty there. He's an expert in quantum field theory in general, elementary particle physics, right? And more specifically, probably about neutrinos. And indeed, today, the talk and the colloquium will be about the Large Neutrino Collider. So the floor is yours.
All right. All right, everyone, thanks for coming. As you can see, I chose a very, very fancy and get your attention title, but the real title is actually boring, but hopefully the content will not be boring, all right? Interrupt me at any time. Again, for the students, just see this as a continuation of the lectures. Hopefully by the end of the week, you're not going to hate me for being talking so often. But yeah, let's start. So before we start, actually, there's a little of a disclaimer that I am part of the DUNE and SBND collaborations. God knows why, but I'm not speaking on their behalf. Whatever is wrong here is my fault, not their fault. So let's start with a very simple question, right? What makes neutrinos so special? And of course, I mean, this is a colloquium. There's a lot of my own personal view. So what I'm going to tell you, many things are not the law. It's what I think, okay? Including the answer to this question. But my answer is 3 words: weak interactions only. To me, weak interactions only defines neutrino from both a experimental and theoretical point of view. And I'll try to convince you of what that actually means in the following slides. So let's start with theory implications, okay? Weak interactions only. What's the deal? So think about particle and antiparticle, right? What defines a particle and an antiparticle? And experimentally is actually very simple. It's charge. Electron, positron. They are identical except for the charge. Proton, antiproton. But neutrinos do not have a charge. And because they do not have a charge, it's actually not obvious that there is a neutrino and an antineutrino. Maybe the neutrino is its own antiparticle, and what we call antineutrino is just a difference in helicity, such that it changes how it interacts. That is to say that neutrinos could be Majorana fermions. And this is the only fermion in the Sano model that can be a Majorana fermion, right? We don't know if it is, but it could be. And one of the most obvious consequences of that is the existence of a double beta decay, where the nucleus changes to another nucleus by 2 units of Z and emits 2 electrons, but one that is without neutrinos. If you see here, if you just count the number of leptons, there were 0 leptons before, 2 leptons. You are violating lepton number by 2 units. This is a clear signal of the Majorana nature of neutrinos. Now, besides that, if you look at the charged fermion masses, they kind of seem all to come from the Higgs mechanism. I've been a bit, not very precise here, but the Higgs mechanism has a very unique prediction that the mass of the fermion is proportional to the coupling to the Higgs. And we have indeed observed that for the top quark, the bottom quark, the tau lepton, maybe the muon within big arrow bars. So, third family does that. Second family looks like they do that. Everybody does that. I'm extrapolating. But it does seem that we have discovered the mass mechanism of charged fermions. But for neutrinos, it's actually weird, because if you just try to do the same thing as you would do for the Higgs, you have a left-handed field, the Higgs, and a right-handed field, you need to add a particle, a right-handed neutrino, which maybe doesn't strike you as like an absurd thing, because you have right-handed electrons, right-handed top quarks, and so on and so forth. But the right-handed neutrino is a very, very, very special particle, if it exists. It carries no standard model gauge quantum number whatsoever. So it does not have any interaction. as far as we know, there is no particle that has no interactions at all within the standard model. So this would be a new particle, a new beast. And more interesting than that, in the standard model, particles do not have a mass unless the electroweak symmetry is broken. This guy, a right-handed neutrino, it could have mass completely independent of the Higgs mechanism. To me, this is actually, although it may be simpler, it would be an alien. It's a particle that does not fit the structure of the standard model. So if you just try to do the same for neutrinos as you did for charged fermions, essentially you get a lot more automatically. Besides, still from a theory point of view, if you just look at the spectrum of fermion masses, so you have here the third family, second family, first family, charged guys, and then neutrinos, we don't really know their masses. We know that the mass splittings from oscillation physics, as we have been discussing in the last days. But that means that we know that some masses need to be non-zero, and we have constraints from cosmology and lab observations that they cannot be very large, like they cannot be above the electron volt scale. There are 6 orders of magnitude gap here. Is that proof of anything? No, it's not, but it just feels weird, right? They are way too light. Neutrino mixing is kind of way too big. If you compare with quark mixing, it's like enormous. And from a theory perspective, if you just close your eyes and say, I'll write a Lagrangian for neutrino masses, neutrino will come out Majorana, right? It's like you got to think carefully to make neutrinos Dirac. It's usually, if you don't pay attention, neutrinos will be Majorana fermions, which is very different from the rest of the standard model. So this is why I think that weak interactions only sort of defines what neutrinos are from a theory perspective. Besides that, I believe this may be something that you'll see in Mateo's talk. Are they going to see in your talk? Eventually you'll see in Mateo's talk. Because neutrinos only have the weak interaction, they are kind of perfect candidates to be a portal to a new dark sector. Of course, that is not proof of anything, but it is interesting. But maybe I'll not talk about this more. Maybe I'll leave to Mateo's. So let me go to experimental implications of weak interactions only. And this is where things actually get fun for theorists. So the interaction cross-section is very small for neutrinos because it's weak interactions, okay? So that means that neutrino sources need to be extremely intense, and the detectors need to be fairly massive, which, in my opinion, can boil down to the following, that neutrino detectors cannot be microscopes. And what do I actually mean by that? Let's take this guy, right? CMS. This is too complicated for me, so let me do this. So this is what I would call a microscope. There is a whole apparatus, super duper optimized, to look at what happens in a tiny region of space, right? So you build things all around that are looking in a region like yay big. Okay? This is a microscope. It means that you can optimize your detector very, very, very much for interesting stuff happening here. And honestly, this is how we do physics, right? When you do like some quantum optics measurements and all that, you're measuring something at like as a point as possible. Even when you look in space, a telescope, I won't say that the telescope is a microscope, but you are looking at a very narrow region. Most of the, in many different telescopes, you may be looking at a very, very specific region of space. So when you do that, your entire apparatus is focusing on a tiny little angle here and like measuring all this stuff, right? Super optimized for a tiny little thing. But now, this is a neutrino detector. It needs to be as big as possible because the cross-section is too small. This is not really there. This is just to scale, okay? So this is the size of the Statue of Liberty inside Super Kamiokande. It's a big tank of water. Neutrino interactions can happen anywhere in this water. and you just put photomultipliers to detect the light around this thing. So you're looking at a volume of 40 meters high by, I think it's about 30 meters diameter or so. This is an enormous volume. This is not a microscope. So that is the experimental crux of neutrino physics. It's very hard to optimize neutrino experiments because you need to be looking all the time at a very, very large area. And this is very challenging. You cannot optimize things for events that will happen exactly here, because the probability that a neutrino interacts in this small regional space here is too small.
Essa imagem à esquerda, ela seria o detector interno, o WIN?
So this is inside Super K, and it's like usually the water level goes to the top, right? But from time to time, we need to lower the water level, like maybe clean stuff, I don't know. But usually Super K has water to the top. So this is inside the detector. You fill up with your water, you close it, and then you leave and you do experimental magic on it. All right, so here are some experiments that we are building at Fermilab. There is first the short baseline neutrino program with the SBND detector, which just started collecting data. Microboon, which already run, and now it's not collecting data anymore. And Icarus, which is collecting data for maybe 2 years by now. And the future Dune. These detectors, what I like about them, and this is, again, it's personal, I do like this kind of detectors very much, is the fact that they are liquid argon time projection chambers, and that gives them a lot of capabilities that I will explain to you in the next slides. So just to give you an idea of sizes, the future Dune experiment will have 40 kiloton fiducial mass of liquid argon, 40,000 tons, in a 2.4 megawatt beam, which will be the most powerful proton beam for high energy physics in the planet, where accelerate protons to 120 GeV, and you detect neutrinos in the near detector, in the far detector, and the far detector is 1,300 kilometers away from a beam. You need these big distances to see neutrino oscillations. And the near detector hall is actually fairly complex and can do a lot of stuff, but I'm not going to go there. So what is the deal about these liquid argon time projection chambers? Okay, so before we go to them, let's have a look at other detectors in neutrino physics, what they look like. So this is an event. It's a bit of an unfair event, but it is an event in the MINUS detector. That is an electroneutrino. You really don't see much, right? It's a bit of an unfair event because MINUS was not really built to measure this. So, you know, but it is what it is. This is state of the art. This is an event at the NOVA experiment, and you can see like clearly tracks of particles and stuff here. So you can actually identify particles and understand the details of the event. That looks way better. Super K, the big tank, you produce a charged particle inside the detector. It emits Cherenkov light. You detect the Cherenkov ring in the PMTs. And by the ring, the size, and the time of the arrival of the light, you can reconstruct where the particle came from and even the position of the interaction. This is an event in IceCube. IceCube is a detector in the South Pole, bunch of strings in the ice. In the strings, you have photomultipliers. A muon, super high energy muon comes here, Cherenkovs, and you detect all this light. For you to have an idea, this is like a kilometer cube volume. So the distance between PMTs is enormous, right? This is not like a small detector, this is an enormous detector. But you can see that you get a lot of stuff there, but you don't get like super detailed information about what exactly happened in the event. Again, mini-boon is again Cherenkov light, like this guy, but at a smaller scale. These are liquid scintillator experiments where light is mostly isotropic. You don't use only this to reconstruct your events, but you see that you do not have so many handles. And this is a liquid argon time projection chamber. So you can clearly see it's a bubble chamber, almost, with colors, right? Bubble chambers were black and white. This is not black and white. And I'm not joking, right? Bubble chambers measured the charged particle crossing. This measures not only that there's a charged particle crossing, but it measures the calorimetry, how much energy the charged particle deposited. That is what gives you the colors. It's not just for fun. So it's a bubble chamber with calorimetry. To put things to scale, this is to scale an event in microboon and an event in nova.
About specifically what, I mean, you're measuring energy.
Sorry, I
what
should
do
have
you
said,
mean?
I should have said calorimetry. So what I mean is you can measure the amount of charge ionized in every point in the detector.
Okay.
That's what I mean by calorimetry.
Perfect.
So imagine a proton, a low energy proton flies through the detector. It ionizes a lot. These electrons drift, and then you measure some current. The largest is the current, the more charge you have ionized. So that's what I mean by calorimetry. All right, so this is the events to scale, and now you can clearly see that like this, I don't know, high definition television. This is one of these big televisions with the stuff behind. I think you guys probably never saw one of those. I mean, you did, I did, but not the kids. There used to be stuff behind the TV. So the question is now like, look at that, right? This is beautiful. I am biased because I really like this kind of stuff, but this is beautiful. What can you do with that? So before I tell you what we can do with that, let me just give you a little bit more on how these detectors work. When you produce a charged particle in this detector, say a pi plus, it traverses the liquid argon, so this is a liquid argon tank, and it ionizes a bunch of stuff. It creates like an electron cloud. If you just leave it there, this electron cloud will recombine, and you don't see much. But you put an enormous electric field, like, for example, in SBND, the difference in tension is about 100 kilovolt, and these electrons drift now. And as they drift, somewhere in the detector there are wires. So the wires collect these charges, and in a single wire, you see a current on time. And then you combine the current over time of several wires, and that allows you to reconstruct the event. I mean, from this to this, there is a lot there, but I'm a theorist. What experimentalists do to me, at some point, it's kind of magic, right, because of my own ignorance. But you can actually go from all these currents and all that to these very detailed events with the amount of energy deposited in every point in your detector. And you can like identify particles from this, right? For example, let's see if I can do that. This guy here is probably a proton because it propagated a bit, it started depositing a bit more energy very, very soon, and is not a very long track. I mean, again, I'm a theorist, so don't trust exactly what I'm going to say. This guy here, you see the gap? That most likely was a photon that doesn't do anything until it converts to any plus and minus pair and leads to an electromagnetic shower. And you have one here and one there. So you have two photons. So what emits two photons? Pi zero. Pi zero decays to two photons. So these two photons point to the interaction point where it produces the pi zero, and so on and so forth. So how can we leverage all this technology, in particular for the Dune experiment, to probe the outstanding questions of the Sana model, okay? That's what I want to answer in the next several minutes. You can just shout and I repeat your question. No?
So you explained how to reconstruct the events, but I didn't understand how do you know an event happened inside the detector to then reconstruct it?
How do you know an event happened inside the detector?
Yeah.
So for example, in these detectors, there are several ways you can know when an event happens. When an event happens, one of the things you can do is that the neutrino comes, create particles, ionize stuff. It emits light. Light's very fast. Whenever you see light in several PMTs, you can say, open up the channels, let's get data. So you can trigger on light. But actually, on this kind of detectors, microboon, for example, and DUNE, because you have a beam of neutrinos that you control, you know that the beam has a timing structure. Whenever there is beam on, you say, collect data. Even if there's no event, you still collect the data. If the beam is off, then you can collect the data or not. You will collect the data to the like stuff. But you know when the beam is on. So these are two ways that you know when events are happening in your detector. Does that answer your question?
Yeah, okay. I was thinking about IceCube because they know the event happened when they have a certain number of PMTs activated. And I was thinking about that, but here you know when the event happened because you are shouting a beam
You
in the
can
detector.
use the beam information. You can also use PMTs, right? SBND, for example, has a bunch of PMTs. When an event happens, it will shine light on these PMTs. So you can actually build a trigger for, say, whenever n PMTs acquired some amount of charge, you turn the detector on. So you can do that, yes.
Thank you.
For DUNE, this will be very important because DUNE can do atmospheric neutrinos. And atmospheric neutrinos, they are coming all the time without a timing structure. So you got to trigger on something that is not your beam. You got to trigger on light. Any more questions? All right. So how do we leverage that? So in what follows, I'll try to give you several examples of how we can leverage specifics of liquid argon time projection chambers to do more physics than we were expected to expand the physics program of, for example, DUNE. So let me start with low energy atmospheric neutrinos, probing CP violation, doing Earth tomography. I do like this Earth tomography stuff very much, although I don't know how useful that is. So it has been shown in other experiments, in like tabletop experiments, one called Argonaut, that liquid argon time projection chambers can actually detect and reconstruct well protons with recoil energy, so kinetic energies, down to 20 MeV. That is very, very, very low energy for a neutrino detector. You can see it here, for example, super low energy proton here. And this means that you can reconstruct, you can identify, and can even point. I mean, you can clearly see a direction of the proton here. For comparison, big detectors like Super Kamiokande, they can only see protons that emit Cherenkov light. So if you don't remember, particles faster than light in water can emit Cherenkov light. And a proton to be faster than light in water, you can do this calculation very easy with the refraction index. It needs to have a total energy of about 1.4 GeV. Below that, the proton just doesn't emit light, and you can't see it. It's invisible. So the kinetic energy here is about 500 MeV compared to 20. It's a completely different business. Besides, it has also been shown that the details of the event carries information. So Argonaut, at some point, was in a beam of neutrinos. And in a beam of neutrinos, what they did is that they counted the number of protons in every event. And this is the number of protons. Don't bother about the big bars, just look at the data points. The big bars are like bad generator predictions. So you see that in a neutrino beam, you really have lots of events with 1 and 2 and 3 protons. But then when you run in an anti-neutrino beam, most of the events have no protons at all. And you can actually trace that back from the elementary interaction, where when a neutrino interacts, it transforms a neutron to a proton, so it tends to get one proton being kicked out. But an anti-neutrino does the opposite, makes a proton become a neutron, and neutrons do not have charge, do not ionize, so they are invisible up to some extent on these detectors. So then, how can we leverage that to do atmospheric neutrinos? Well, let me tell you why low-energy atmospheric neutrinos are interesting. So this is the oscillation probability for a bunch of channels. Don't bother about the details. For low energy, like below the GeV atmospheric neutrinos. And this is what you have for nu-mu to nu-e oscillations for beam neutrinos, okay, like at DUNE. And what I want you to look is the difference between the red and the black line. This difference is the amount of CP violation that you get. These are 2 lines for different values of the CP phase. And if you look here, it's a 2% change, absolute change on the probability, okay? If you go up here, the CP phase shows up as the difference between the green and purple lines. And if you just shoot it over there, that's like a 10 to 20% effect. So it's an enormous effect. And of course, you can say, well, if the effect is that big, why do we actually need a beam? And the reason why we need a beam is because these sub-GeV atmospheric neutrinos are real hard. When a neutrino comes and interacts with a nucleus, let's say it kicks out a lepton like a muon and a proton. If you look at that in a Cherenkov detector, I just told you that a proton with less than 1.4 GeV does not emit Cherenkov light. This neutrino, let's say it has 1 GeV. Most likely this proton will be below the Cherenkov threshold, so you don't see that. Now, if I take, say, a half a GeV neutrino hitting a 1 GeV nucleon, the thing that come out is not going to be super forward. It's going to have a large opening angle. So when you measure what you can measure, which is the muon, you actually do not know where the neutrino came from. The uncertainty is like this. So if I do this here, it could either come from like crossing the Earth or not, which means that when you try to reconstruct these curves, there is a similar curve for different zenith angles, and you are summing them all up because your angle uncertainty is super bad, and you just smear out all the CP violation effect. So that's why Cherenkov detectors just can't do that. Now, large TPCs can, as we just discussed it. So we locked ourselves in a room for many days, and we did an analysis, and I'll spare you from the details. We tried to be as careful as possible with as many systematics and detector effect as possible. And what we saw in the end is twofold. One, that imagine that you assume that CP violation is the thing that T2K has been hinting on measuring, 3 pi over 2. We can actually rule out several values of CP above the 3 sigma only doing that. That's for free. We just need people to do an analysis, but you don't need to build anything extra. Besides, when you look at events with, say, 1 proton in the final state, you get this kind of sensitivity curve. When you look at no protons or several protons, you get this one. If you sum them up, they're like down here. But when you combine them in a single analysis, it boosts your sensitivity because these different events, they are looking at complementary things. And that makes your analysis way better. So this is very exciting to me, that you can have access to CP violation independently of the beam. Even if the beam has systematics and possible mismodeling of neutrino nucleus cross-section, which is a hard problem, this is an independent check of beam neutrinos. The other thing you can do with that is the following. When neutrinos cross the Earth, or any matter for the case, they feel a refraction index, just like light on water, right? And if you feel this refraction index, there is an imprint on neutrino oscillations. So when you look at neutrinos coming through the Earth, if you know the direction of the neutrino, you can try to reconstruct the amount of matter the neutrino went through and the profile of this matter. And by doing that, you can try to measure the density of the core, the inner mantle, and the outer mantle of the planet. We do have measurements of that from geophysics, but most of these measurements, they they depend on several, how do I say it? They depend on things without error bars. That's as good as I can say. So this is a completely independent check of that. And earthquakes, I don't know if you know how earthquakes actually measure this stuff, right? It's like when you have an earthquake, there is a wave. There is actually several kinds of wave. There is one wave which goes like this, and one wave which goes like this. The wave that goes like that, it's like a sound wave. It propagates on water, for example, or solids. And these waves, whenever there's an earthquake here, you see them down there. But the waves that go like this, they need to have a solid structure to propagate on. They do not propagate on liquid, and you actually see a shadow of the core, so you know that the core is liquid. The way these waves propagate depends on empirical relations about the speed of waves and the density of whatever they're traversing and so on and so forth. And by measuring lots of these earthquakes in several places, you try to reconstruct the profile of the density of the planet. Here, so with earthquakes, you're measuring the density, the mass density. With neutrinos, you're measuring the weak charge of the planet, which is pretty neat. The weak charge of the planet is essentially the number of electrons. So when you measure earthquakes, you're doing protons plus neutrons. Earth is neutral, to a good approximation. When you do neutrinos, you're doing electrons, that is protons. So by comparing protons plus neutrons with only protons, you can actually try to infer if the core of the Earth has a high Z over A, like metals composition, or if it's 1-to-1. And again, doing a detailed simulation, this is what we get, that you can measure the density of the core, the lower and the upper mantle at uncertainties like of order 10%, which to me is pretty neat. I don't know what that's good for, to be honest. If you think about an application, let's talk. But I just think it's very curious. So let me give you another example. Actually, not an example. I'm telling you all this magical stuff and how great this detector are. But let me take a step back and tell you about some problems, right? There's always a challenge. And one of the main challenges to unlock all this physics is to understand the neutrino nucleus cross-section modeling. Here's the deal. When a neutrino interacts with a nucleus, the modeling this interaction is actually very challenging. You depend on the nuclear configuration, that is the momenta distribution of the nucleons inside the nucleus. You depend on the cross-section itself for the neutrino nucleon scattering, that is the form factors and stuff. Hadronic excitations, like you could excite, say, a proton into a delta resonance, and these processes are non-perturbative, so it's hard to calculate them. You got to propagate pions inside the nucleus, and now you get strong interactions playing the game. You got to propagate the hadrons throughout the nucleus, because the nucleus is quite dense. It's not obvious that when you kick out a proton, it will just exit. It might hit something and give you stuff out. And then there's a nuclear remnant, which can emit photons, for example. If you kick a nucleus, and it ends up in some excited state, it will decay, emitting photons, which you can actually see on these detectors. So it's an area that involves nuclear physics, neutrino pheno, because you got to know what you want to measure, lattice QCD for inputs like form factors, effective field theories for dealing with pions propagating on a medium, and generator technology to actually give a product to experimentalists to be able to compare with what they measure. Making a long story short, this is the status, the state of the art of this field. Oh, always forget this thing. All right, this is the status of the art of this field. This is the data, and the black and the dashed are two theory predictions, and they suck. Like by 20%, 30%. So this is where we are right now. It is not good. If we don't get this properly, we are not going to leverage all the marvels of liquid argon time projection chambers. So this requires a lot of people with a lot of expertise on different areas to get together and solve this. We are actually starting to work on that. At Fermilab, we have a new event generator called Achilles. And these are preliminary results. It's like we do not expect to explain this because we do not have the physics yet implemented to explain that. But you see that our agreement with the peak, which is the only thing that is implemented right now, looks way better than the state of the art. Again, I won't say that our thing is way better than everybody else, because until you implement all the moving pieces and you compare with as many observables as you can, you shouldn't really like claim much. But it looks good. So let me go back to fun stuff with large TPCs, okay? Energy reconstruction. Neutrino oscillation, as we discussed it, I'm glad we erased the blackboard. As we discussed it, the oscillation probability typically goes like some mixed angle and some phase that depends on the neutrino energy. So measuring the neutrino energy is crucial to measuring neutrino oscillations. But I told you that the detector sees a lot of stuff, but the stuff that comes out from a neutrino interaction depends on complicated theory, right? So it's not obvious how to reconstruct the neutrino energy. Like, neutrons are fairly invisible. There are particles which they might be produced, but they are below threshold. You will not see them. And you gotta like take all that into account when you're inferring the neutrino energy from what you measure in your detector. So if you look at this with a bit more detail, there's actually a lot of correlations between the neutrino energy and things that you see. This is a very busy plot, but is a correlation matrix between the neutrino energy here and a bunch of stuff that shows up in the event. For example, lepton energy, proton kinetic energy, neutron kinetic energy, which is invisible, opening angles between leptons and protons, and so on and so forth. And you can see from like the mostly red or mostly blue blocks that there is a non-trivial correlation or anti-correlation between several of these observables. Now, we do not understand the theory well enough to leverage that, but because we don't understand all these correlations, but there is a tool that is ideal for discovering correlations and leveraging them, which is machine learning. So what we did is, I think I already said that, right? Like neutrons are invisible, binding energy adds up for every single particle that is emitted. Excitation energies are hard to excitation energies are hard to reconstruct, so on and so forth. So what we did is to apply machine learning algorithms to neutrino events, simulated events, and see if machine learning can figure out these correlations and give us a better estimate of the neutrino energy, okay? So we fed like tailored mock data to a dense neural network. It's actually a fairly simple dense neural network. I don't know if everybody here under 30 worked with machine learning. If you never did, do it for a weekend. You can actually write a dense neural network like that in an afternoon. Python is magical. It's pretty straightforward, right? I'm just saying, like, if you never try it, just give it a shot. You might have fun at it. And we label the neutrino energy for beam neutrinos and energy in direction for atmospherics, but there's a detail. We train the machine learning algorithm, and this is what we get. So this is a little bit of a busy plot, but let me try to walk through this thing. So the gray line here is the energy resolution that we get when we just add up the visible energy. So for a 1 GeV neutrino, when we just add up the energy of all the visible stuff, we get about 20% energy resolution. For a 4 GeV, we get maybe like 17% or so. And the only line I want you to see is this DNN0N. So this DNN, the dense neural network, and no neutron information whatsoever. I'm dropping the neutrons. I don't care about them. And you see how much this gray line is pushed down, right? Just because the machine learning algorithm is understanding these correlations and extracting more physics for us. You can do the same for atmospheric neutrinos, and in atmospheric neutrinos, you also get an improvement between the calorimetric and the DNN, the two solid lines. We tried to get an improvement for the direction. We failed miserably, but that's life. Maybe you just don't have enough information for that. Machine learning is strong, but is not magical, right? It can't create information where you have no information. If it does that, it means that it's doing something wrong. And what this means for the experiment is the following. This is what Dune was supposed to measure when it starts running for the new mu to new mu disappearance channel, but with the improved energy resolution, it gets way more peaked. And there's even one thing which is kind of fun. If you look here, can you see a little kink here? I mean, now that I pointed, I guess you can, right? But this little kink there is the following. This oscillation probability goes down. Just look at this. As you lower the energy, the phase grows. It goes up, and then it hits 0 again and goes up. That's the second oscillation minima. That structure comes from the second oscillation minima. You can't really see that very well because it's a small feature, but you can see that without the machine learning, you cannot see like the kink. Here you can see a little bit of it. It's almost super exciting, so that's life. This is what it means in practical terms. You can get, if you try to like measure stuff like CP violation, by using these machine learning techniques, you can get an equivalent of exposure increase of 10%. 10% may not sound like much, but Dune has 4 FAR detectors. 10% is a little bit less than half of a FAR detector. Each FAR detector is like, what, 500 million? So this is like 200 million, right? I mean, I'm accepting 10% of that as a commission. That's fine. But it's doing stuff increasing at 10% here and there that we can push the experiment to the extreme. Let me give you one more example of how we can leverage large TPCs to do new physics, or to do more physics, and then I can wrap it up. So let me talk about something completely different now. Let me talk about light dark matter at Dune. So we search for dark sectors in liquid argon time projection chambers. So here is a theorist approach of how a beam neutrino works. If you have been here in the classes, you have seen that already. But here's how a beam of neutrinos work. You shoot protons in a target. A target's like a slab of metal or something. You have magnetic horns that will, so when you shoot that, you get pions and kaons. Magnetic horns will focus these pions and kaons. They fly through a decay pipe that is made so that these pions and kaons decay to neutrinos. Then there's a lot of dirt that will absorb the muons, and now you have like a pure neutrino beam. And then you put your detector there, okay? I'm not caring about the far detector right now. I only care about the near detector for this. So what could happen, I don't know if nature chose that, but what could happen is that sometimes when you create pi zeros could decay to photons in a new particle, a dark photon, which then decays to dark matter. And now you have a beam of neutrinos and dark matter. That is a possibility, and it could explain what is dark matter. Now the question is, how do we measure that in Dune? So maybe we have been producing dark matter and neutrino beams all along. We have always had dark matter beams. But measuring dark matter on the neutrino background, right? The neutrinos are my signal when I do neutrino physics, but when I do dark matter physics, they are my background. It's actually not trivial. You got to disentangle your signal from the background. So here's how it works. If this dark matter interacts via this dark photon, it can kick electrons fairly hard. And the main background for that is when a neutrino hits a nucleus and it creates like electrons and stuff. But if you have ever been in a mosh pit, and if you didn't, I do advise you, just don't quote me on that. When a small person jumps in a mosh pit full of like thermal energy, you go out in a random direction, right? But if you are a very, very big person and there is only one person in a mosh pit, and you just go there and jump on the person, which is not a nice thing to do, the person goes forward. So because this guy is light compared to the energy of this dark matter, this electron would go very, very, very forward, while electrons created from this would actually go way more isotropic. No, this is not standard model. This would be an...
But are you calling dark matter anything that's not in the standard model? Or what's your meaning for dark matter?
So what I'm calling, okay, so that could be the dark matter that is needed to get the right dark matter abundance and all that, but it doesn't. The only thing you need is something that is created from pi-0 decays, something new. Like this guy could decay in a microsecond, could be part of, say, a dark sector or whatnot. It does not really need to be the dark matter that explains our universe, but it could, right? It's more general than dark matter if you want. So you can use the LRTPC capabilities of looking at low energy hadrons that are not present here and directionality to actually kill this ginormous background and look for this. So in a nutshell, again, you lock a bunch of postdocs in a room and for long enough. I think when I did that, I might have been a postdoc still. But I just remember being locked in a room for long enough. We do a simulation, and this is what we get. These are the coupling of the dark matter. We parameterize how much you produce that from pion decays. This is the mass of this dark matter. Sorry, the mass of the dark photon, and we just put some correlation between these two masses because you have too many parameters showing 2D. These are the current constraints in gray. This is Dune if you do not do anything very fancy, and the solid line is Dune if you leverage one very special thing about the near detector, which I didn't mention. The near detector of Dune is supposed to be on rails. I mean, this is for real. It's supposed to be on rails so that it can actually move, right? I mean, this may sound very dumb, but it's actually very smart. So this is the deal. When you produce a neutrino beam, when you look in the forward direction, you see a spectrum of high energy neutrinos. As you go off axis, the spectrum of neutrinos go to lower energies and gets more peaked around a specific energy. So by moving the near detector perpendicular to the beam, you're scanning your neutrino flux. And that helps you to understand better neutrino nucleus interactions, which will translate into energy reconstruction. But if we go back here, pi pluses are focused and decay to neutrinos pretty much in the forward region. Pi zeros, they're not focused. They decay to stuff like photons and dark photons and then to this dark matter, which is much more isotropic. So the forward region will have way more neutrino background than the off-axis region. So now you can actually have a measurement where you do background-rich measurement, signal-rich measurement. And when you do that, you get an improvement of almost an order of magnitude in your like naive estimate for the sensitivity to dark matter. So I don't think I have more time, right? I mean, I don't want to like bother you with like 1 hour sharp. So let me jump tau neutrinos. Tau neutrinos are super fun. But here's the take-home message, okay? If you're sleeping, it's, well, you can wake up if you want. So what makes neutrinos so special, in my humble opinion? Weak interactions only. It has deep connections to both theoretical and experimental neutrino physics. It connects to the nature of neutrinos, Majorana versus Dirac, to the origin of neutrino masses, to possible connections to dark sectors, and also it defines the size and design of neutrino experiments, like the intensity of neutrino sources, and so on and so forth. DUNE and the SBN program, which are both LRTPC, liquid argon time projection chamber detectors, they will be a multi-purpose programs. Given the amount of details they can reconstruct from experiments, it just pushes the amount of physics they can do. And the LRTPC technology, in my opinion, is transformative. We are reconstructing neutrino events in a way that we never did before. And it has a lot of potential, but it's far from being a done deal. Like, there's a lot of new ideas coming up. This list has not been updated, and I don't want to write a laundry list for you on this, but there's a lot of new ideas. Although, there is one challenge, right? If you want to unleash this power of LRTPCs, you do need to understand the physics of neutrino nucleus interactions, which involves complicated, non-perturbative physics, and nuclear physics. You can't do it alone. I can't do it alone. You need a team of people working together, theorists and experimentalists, to be able to solve this problem. So we do need new ideas, new approach. Now there's a lot of machine learning. It's one new idea, it's one new approach, but there are many other possibilities. We do need expertise from different areas, and we do need collaborations between theorists and experimentalists. So with that, I can finish. Thank you.
Okay, thank you very much for this colloquium. Now, more questions.
So I have a question regarding the sub-GeV atmospheric neutrinos in Dune. So how can we disentangle the matter effects from delta CP, and due to the directionality for which range of zenith angle that the sensitivity is better for delta CP? And do you know if there is a range that is preferred to look at?
So I know the following. Here's what I know. I know that the effect of delta CP is very, very broad on energy. So if you look here, the difference between the green and purple lines, it's like you have a sizable difference from 250 MeV up to 700 MeV. So as long as you look below the GeV, there is a big difference. But if you look at this plot, what happens when you change the zenith angle, the green and purple lines, they are like this, and as you change the zenith, they might cross in the opposite direction and go back and forth in such a way that when you sum them up, they kind of average out pretty much. So you do need to distinguish the zenith, but you need to look at all the zeniths. Like, if you just look at, say, zeniths that give you, let's say, horizontal-like events, you just do not have enough information to disentangle all the physics. You need to look down, you need to look a little bit here, you need to combine the whole data to get this sensitivity. So it's not a trivial problem, but if you can do that for one zenith, you can do for any zenith, right? These detectors are fairly isotropic. Not completely, but fairly isotropic.
More questions?
Let me finish. Ô Pedro, só em relação ao tau, o Dune promete medir tau, né? Queria saber assim, como seria o padrão de luz do tau?
Okay, so for tau neutrinos are very hard to measure because you need more energy than you want to produce a tau. Like, you need enough energy to produce a tau, but then when you go to these high energies, you just don't have no taus anymore because you're shutting off oscillations. But what you need to do to measure tau neutrinos is to measure what comes out of the tau decay and distinguish that from just any neutrino interaction. So you need to use techniques where you look at something, let's say 3 pions in a final state, that you look at these 3 pions and say, this is way more likely that it comes from a tau than that it comes from neutrino deep inelastic scattering. And to do that, you can use like machine learning, or you can just use like LHC-like techniques, like defining jets and invariant masses and so on and so forth. But as of right now, it's not completely obvious how to measure tau neutrinos at Dune. It is a challenge.
For these dark matter searches, you are using only linear detector, or also your plot take into account far away?
No, I'm only using the near detector.
For both? For both cores?
For both lines, yeah.
Okay.
Where is that? Yeah, for both lines, I'm using only the near detector. In this line, I assume that the near detector does not move and takes data for 7 years. This line, I assume it does move and takes data for 7 years.
Okay.
So that's the only difference. I should have assumed 20 years, not 7, but.
So that was a very nice talk. I just wanted to ask about the time. Maybe it's similar to her question. When is the peak of results going to come out of Dune? Is it in 7 years?
So Dune is supposed to start taking data in about, what, 2032, I think. And it depends on the kind of physics you want to do. Whenever you have a near detector and the beam, in 1 year of Dune running, we are going to get like 5 million events. So we can do nice BSM physics and cross-section physics in like 1 year and when it starts running. For oscillation physics, it may take a little bit more, although like oscillation measurements like the easy ones, like the atmospheric mass splitting, in 1 year we can get a very good measurement of that. The CP phase may take like a couple of years. The neutrino mass ordering, if the third neutrino is heavier or lighter than the other two, that in 1 year we are probably going to have like 5 sigma. So that will be like spot on from the start.
Hi, Pedro. Very nice talk. About this current nuclear-related uncertainties for the neutrino-nucleus interaction that you would need to constrain well enough to get everything you can get from Dune. What do you think would be like the top 3 sources of uncertainty we really need to pin down?
So I think the top 3, and this is really a waving hands argument, right? Don't quote me on that in a paper. I'm just saying what I think, but I could be wrong. I have been wrong many times. I've been known to be wrong very often. Is the top 3, I would say, is the number of outgoing protons versus neutrons, because neutrons are invisible and protons are not. So at the moment that you think that you got more neutrons out than you actually got, you're going to have a bias in your energy estimate. And that bias may actually bias your delta CP measurement. So neutrons versus protons. The overall energy in hadronic, which is related to that, but not exactly, because hadronics, the hadrons are harder to reconstruct. And probably the transition between the resonance cross-section and the deep inelastic scattering cross-section. In deep inelastic scattering, neutrinos see quarks and gluons. In the resonant cross-section, neutrinos scatter on nucleons and create heavier QCD resonance like the delta or the Ns or the sigmas. But the transition between the two things, physics does not really distinguish things like that, right? There is a smooth transition there, and this smooth transition is extremely challenging. We really don't know even like the size of the error bar for that. So I think these will be the 3 main problems.
So I have 2 questions. I'll ask them in a row. So the first one is that Dune will solve the mass hierarchy problem, right? Do we expect another experiment to do so before Dune? We expect, for sure, a combination of experiments to do that before Dune. We expect a combination of Orca KM3net, so that's atmospheric neutrinos in the Mediterranean, plus ice cube deep core, that's ice cube in the South Pole, plus Juno. The combination of these 3 will give us mass hierarchy at 5 sigma, most likely. If they all run well, and if the data all agrees and all points the same direction, which is a big if. For a single experiment, there is the possibility that Juno can do that alone, but it's not completely obvious. So Juno is an experiment in China where the goal is to measure neutrinos emitted from a reactor core about 50 kilometers away from this reactor core. And if you just look at the oscillation probability that they'll see is something like this. It's pretty neat. Where the big wiggle, that's a delta m square solar-driven oscillation. And the small wiggles, this is a delta m square atmospheric. The phase of the small wiggles, if they're a little bit more to the left or to the right, they give you the mass ordering. But to do that, you need to have an exquisite energy reconstruction that no experiment ever had that. I'm not saying that it's impossible, but it's a challenge. And nature needs to be a little bit kind to you because the size of these wiggles strongly depend on oscillation parameters that have been measured but have error bars.
So there is actually room for, if we are actually a little bit, let's say, to the right of the error bar in certain parameters, they might be able to do this above 3 sigma. But if we are on the other direction, they might not even be able to get to 2.5 sigmas. They will not get to a 5 sigma measurement, but then we can talk what is a measurement, what is not a measurement. But yeah, Juno, the promise that they will do that after, I think, 6 years of running at the 3 sigma scale. But they need the energy reconstruction, and they need to be a little bit lucky with oscillation parameters, or at least not be unlucky.
Thanks. May I ask the second question? So you said that it's crucial for June to understand the neutrino-nucleus interaction. Does understanding this interaction much lower energies, like nuclear reactor energies, help in any way?
It does not. It's not a bad thing. It helps in some senses. There is stuff, for example, you can estimate, like, the binding energy of a nucleus is about 30 MeV. The energy that we're talking of neutrinos is 3 GeV. If we start talking about, let's say, several particles in the final state, you could easily lose like 80 MeV or 100 MeV to binding energy. So this is related to low energy physics. There is also stuff that I did not talk about that Dune, like supernova, which if a supernova happens, Dune will detect neutrinos from the supernova, like copiously. And these energies are at the, say, field to 30 MeV. So it has some non-trivial overlap with reactor spectrum, which goes up to like 8 MeV or so. So there is stuff there which will be relevant, but is not a clear one-to-one connection.
Hi, Pedro. I've just recently heard that the Shannon experiment has measured solar neutrinos via sevens with about 3 sigmas. Can you comment the consequence of this?
So I heard during lunch that they just measured that.
So do I. I just received the image here.
Oh, you should send it to me because I still didn't receive an image.
Okay, I'll show you later.
So this is actually very interesting. So what this is, for those of you, well, I think most of you were here during my lecture, but dark matter experiments, they look at dark matter hitting nucleus very softly. Solar neutrinos can do that. This is called the neutrino floor, where solar neutrino interacts coherently with a nucleus in a dark matter detector. We have never observed that. And I remember very clearly saying in the lecture that first we get there, and then we try to beat it. Apparently, we got there during lunch, so it's time to try to beat it. So what is the impact of that? I think you can say that this is it's kind of a cornerstone for dark matter experiments. If you had like landmarks on, points where dark matter experiments should like do a party, that would be one of them. Now, we have seen solar neutrinos already. We know they're there. We have measured coherent neutrino nucleus scattering. We know it's there. So this is a known background. It's not unexpected that they measured that. And as far as I understood, they measured something consistent with expectations. But it's, in some sense, a new era for dark matter direct detection experiments because they're getting to the point that they will become dark matter and neutrino experiments, right? So they need to worry about neutrino physics now for solar neutrinos. That is very exciting, to me at least.
So thanks for the nice talk. And my question is regarding the energy reconstruction and resolution. Because from your plots, it seems that it rises quite quickly as you go towards low energy. So I want to know, what should I expect for MeV range? Like, oh, it is in MeV, but 1,000
Well,
MeV.
yeah, this is like 500 MeV or so.
Yeah, so what scale of energy resolution should I expect for solar neutrinos or supernova neutrinos?
That's a great question. This curve does not extrapolate to 0 easily. Because what we are seeing there is the calorimetric energy, that is all the deposited energy, when you have what we call a quasi-elastic event, when a neutrino hits a nucleon on a nucleus and a bunch of nucleons come out. The reason why this is super bad is because many times a neutrino will kick a proton, which then will kick a neutron, and neutrons are invisible. And if you have little energy, you will essentially lose your entire hadronic system, so you're dead. If you go to higher energies, you're typically kicking out like several protons, maybe making a pion. If you lose one of those, it's just one out of several. So this is why this curve gets real bad when you go down here. But when you go to like really low energies like supernova, the detection process is actually different. The detection process for supernova is this: neutrinos interacting in argon-40. Because they're low energy, they don't see nucleons, but they do this. They emit an electron and give you potassium-40 star. And then this guy, I think this is it. You should check. Yeah, that's exercise number 11. Check if this is really potassium-40. Maybe you can check now, but well, whatever. Is it potassium-40? I think it is, right? I think it is. I was never very good at chemistry. And then this, what I know is that it's an excited state here, and this guy emits a photon. So when you have this stuff, because this nucleus is much heavier than the energy of the electron, the mass of the nucleus is much higher than the energy of the electron, this guy carries all the momenta, and this guy decays down to a ground state in a photon, so all energy is actually visible. This you have for both supernova and solar neutrinos. So for supernova and solar neutrinos, there is actually very little energy that is missing. It is not trivial to reconstruct this, because this is like a few MeV photon. And this guy will be a 20 MeV electron or 15 MeV electron. So this is challenging, but there is very little missing energy. So if you can identify and reconstruct that, you would expect this energy resolution to actually be way better than what you have here. So energy resolution depends on how you detect stuff. And since the process is different, it doesn't extrapolate down.
Okay. Oh, last minute question.
Thanks. Could we go back a few slides to that 10%? What was it, like $200 million gain?
Oh yeah, true. My 20 million.
Oh, 20. Okay.
I mean, this is just the amount that I would accept. Oh, sorry, that was on the.
Oh, maybe it was the other direction.
Yeah.
Yeah. Sorry. So where does the 10% gain come from? How do we actually get it?
Oh, that's just because if your energy resolution is better.
Yes.
You can get stuff like you can improve the knowledge of theta 2-3 very much.
Okay.
Delta M square very much. And these things will translate into small improvements on delta CP at the 10% level. Like, at the 10% level means when I get an exposure for the standard stuff, and I see how much, sorry, when I require a sensitivity to delta CP, and I see how much exposure I need with the standard stuff, and I compare to the exposure I get with the DNN, I get a 10% increase, right, or 10% decrease. That's essentially it, right? So because you measure parameters better, you need less data to reach the same sensitivity, which is equivalent to 10% less exposure to get the same sensitivity.
Okay, thank you.
Sorry? Well, efficiencies, we are taking all of them to be the same. Because like you do the DNN after you reconstruct stuff in your event. So that's just a last step on the analysis, right? I don't think at least if you do the DNN the way we did, you do not touch efficiencies. You need to do something else for efficiencies. Maybe it's another machine learning thing, but hopefully not one machine learning where we try to do everything at once, because that is probably not a good idea.
Okay, so thanks again,
all right,
Pedro,
thank
for the talk.